Okay, sorry about that, everyone. So this talk will be a little bit different. It's not really an HPC talk, but and I'm not going to have scaling graphs and comparison of this performance versus that. I'm not going to have any of that because this is all a program that's being written for a very specific purpose using Legion, and that's to support what we're calling the radio camera to do real-time imaging in a new facility that's being built called the DSA-2000. So this is work in progress. It's not done. I have prototypes, but there's a lot of stuff left to do. By the way, I'm Martin Pokorny. I'm a staff software engineer at Caltech, but don't go looking for me in Southern California. I live in New Mexico, where I previously worked for the National Radio Astronomy Observatory, and still live there. This I should say before I go on, this project is being led and built by Caltech in cooperation with a group called Nanograv, which you may have heard about last year when they announced the low frequency gravitational wave background that was detected. So this instrument will contribute to that, where they've had a lot of problems since Arecibo collapsed. We're gonna help them with that. And we're being funded, it's been cut off on this slide, by Schmidt Futures. Originally, it was NSF, but they don't have money. So what is the DSA-2000? It's a new project. Like I said, we're building an array. It's going to be in central eastern Nevada near a town called Ely, primarily chosen because of lack of cell phone coverage in the area. It's going to consist of 2,000 fully steerable 5-meter dishes with a frequency range of about 700 megahertz to 2 gigahertz. And it's optimized for surveys. Okay, so one way we're pitching this is, if you're familiar with the LSST or Rubin telescope that's coming online, becoming operational in South America. They've been working on it for a long time, spent a lot of money on it. We're the radio equivalent. So we're going to conduct a full sky survey over a 5-year span. Construction is slated to start in 2026. We're currently building prototype antennas right now. First light before the array is completely finished should be in 2028, and then late 2028 we'll start the full sky survey. So like I said, this is optimized for surveys. If you look at the graph here on the right with the sensitivity, so what kind of signal can you pick up on the horizontal axis and survey speed on the vertical axis. The DSA-2000 exceeds the survey speed of any planned or existing facility by an order of magnitude, and is pretty darn close in the sensitivity as well. So a lot of these instruments here are not even built. SKA mid, for example, that doesn't exist. NGVLA doesn't exist. The survey is expected to discover more than 1 billion radio sources that will increase the known population by over a factor of 100. So we expect it to be very productive. There's stuff about transient phenomena as well, but I'm not going to go into that because it doesn't really have anything directly to do with the radio camera. But all this it's one of the things that attracted me to this project is it really is an integrated project where it works because of all the different parts that have to work together. But in terms of technology, the two key things are the radio camera, digital backend, and a cryogenic-free antenna and receiver, which brings down the cost to where you can actually build this. So what's the radio camera? So this is kind of this is a picture that is meant to describe the data flow from the antennas to images. Okay, so we start with the antennas on the left. They are connected to a central building by fiber. We send RF over fiber where it's digitized, channelized by what we call the radio camera front end, and then the data are sent. So on the left, for one antenna, we have all the frequencies, and on the right, through just a network switch, we now have in each of the horizontal lines, we have one or a small number of frequencies from all the antennas. In the dotted box is what would normally be termed a correlator in radio interferometry. And that big vertical arrow on the right is what's called is the visibility data. That occurs right after the cross multiply step. The visibility data is typically the last step in the online data processing of radio interferometers, okay? At that point, the data are dumped out the disk, and then you have to turn on that very expensive computationally to create an image. We're going to bypass that, and I'll explain how that works. So the motivation is the following. The amount of data you produce, the visibility data that you produce scales as the square of the number of antennas. So what are we doing? We're putting in 2,000 antennas, which is, you know, 1 or 2 orders of magnitude bigger than anybody else has done. And so our data rates will be very huge. If we were to save that visibility data, we figure it would cost about 20 exabytes a year. And the storage cost of that would be comparable to the complete construction cost of the entire array, which, you know, we're not building a computing facility. Well, we are, but we're building an instrument to do astronomical research, right? Typically in projects like this, 10% or so, 15% of the cost will be dedicated to computing, right? So that doesn't work. So what are we doing with 2,000 antennas? Well, here's the key. So on the top row, we have the VLA, where I used to work. It has 27 antennas. This is in a compact configuration. And this is a very poor rendering of the DSA, which shows way too many things in here, makes them monstrous. They're not that big. They're probably hundreds of yards apart on the ground in actuality. The point response of this instrument to a point source in the sky is what we call the point spread function up here. And you can see it's got the central point and then spokes radiating out. That's pretty typical. That's totally defined by the geometry of the antennas. If you take an instantaneous image of the sky with that, you know, you get the sky convolved with that. So it looks like the upper right image. So then if you have your visibility data, you take it offline and you do all the work and you do deconvolution processing, you might end up at the bottom right. Okay. In our instrument, the point spread function looks more like an ideal Gaussian. And so we get something like the lower right immediately without requiring deconvolution. This allows us to create a deterministic streaming pipeline that will create images in real time. So some of the details here, I'm gonna talk a little bit more about this later, but there's a high degree of data parallelism. You know, we split everything up into channels like that image, that diagram showed. And then we can pretty much treat almost every channel can be processed independently. That's not entirely true, but I'll get to some of that in a minute. The total input to the radio camera processor, so that's after the front end, after the corner turn, is 43 terabits per second. After we do all our imaging in the radio camera processor, it outputs at about 23 gigabytes per second. There's a lot of different images. We produce an image basically every 10 minutes in like 12,000 different channels. That's correct. That's correct. Yeah. Yeah. So at different points in this processing pipeline, I just named these things. I won't go into details. There's you know a fair diversity of the different data types being used here, and the rate at different points of the flow that we need to deal with are listed on the right there. So this is very much a through, you know, we're going to have to create a very much throughput optimized system here. I don't really care too much about latency except for the fact that it uses memory. All right, so we're bound. We have a good hard bound with latency, but we need to reduce. You know, we won't be buying expensive high-end GPUs, right? We can afford that probably. So we're actually targeting sort of the, you know, the workstation class GPU, but it mounted in racks. We're trying to achieve a goal of processing 4 input channels per GPU. I should emphasize that's a goal. We don't actually know that we can do that yet. And we define things called the subband, which consists of 20 channels. And for for maximum parallelism and reducing or eliminating internode communication, we want to put all those channels on a single node. If you add it all up in the radio camera, that means we're going to need to use about 3,800 GPUs. There are other parts of the system, fast time domain stuff, and that will raise that total figure to more like 5,000. Okay, so we're going to build this in a small valley in eastern central Nevada, a nice data center that we have to put up. Another way we're reducing costs is the image output from the radio camera processor will actually be the local disk, setting up a distributed file system, which all the nodes can write to, is more money than we want to spend on that. There is processing. I should emphasize that one picture that I showed, which said, look, we don't have to deconvolution. That's a bit of a white lie, okay? There are imaging artifacts in those images that will come out of the radio camera processor, but they can be corrected using image domain deconvolution, which is a much faster, simpler process than the visibility domain deconvolution. That's traditionally done. So all this works in a Legion program that I've been working on for a couple of years now. We're going to call it Synthesis Imaging Camera, or SimCam. I want to talk mostly about how we're trying to, achieve some kind of real-time responsiveness or performance out of Legion program. And there are really two inputs we need to consider: the data, which I've been talking about, but there's also events. Okay, this is part of an operational system. It's not always going to be doing the same thing. Starting to do imaging over here. Oh, wait, now we're going to move the telescope over there. I'm not going to be doing imaging in between, right? There are specific sorts of calibrations that might have to occur. Engineers, keeping 2,000 antennas going over however long the thing exists. There's going to be continual maintenance. We need to be able to diagnose problems, and oftentimes the best place is to use some of the data that's available already in the radio camera before the images are produced. So as I said before, in every channel, data arrive for all antennas. Okay, so there's a big gather going on there. The data are packetized, but I say the antenna multicast. It's not actually the antenna. There's a radio camera front end, and it's going to multicast via UDP. And the raw data are sampled at 7.5 microsecond time resolution, but it's packetized into bigger chunks. And the data come in with identification, most critical being, for example, a timestamp to what I'm going to talk about, but also, of course, which channels am I? There's a lot of emphasis throughout all of this in flagging bad data. We don't really care so much if we lose a little bit of data here and there. It doesn't really matter. That's pretty common, interference, equipment goes down or whatever. If I drop a network packet, I don't really care so much as long as I can deal with that fact. All right, so but what ties these two things together is the timestamp in the data, and the events have kind of a time with them too. When does this thing occur? How long does it keep occurring, for example? So we need to somehow get those input data streams into Legion region instances. And so we actually do we receive both the events and the data in dedicated threads, okay, that are completely outside of the control of the runtime system. They just run, taking the data as it comes in. And then we have to launch Legion tasks at the top level that provide instances of regions which then get into which the data or the events are copied as needed. There are a few real-time conditions here. There's data timeout. We can't wait endlessly for data to arrive. At some point, we have to say, no, it's too late. We're moving on. That's pretty easily done. If I'm waiting for data at some time value and I'm getting data from a much later timestamp, I'm going to stop waiting for that other data. There's also event deadlines. Similarly, the events tell me what to do with the data once I have it. I can't wait. I can't stand around forever holding on to some data saying, what am I going to do with this? Okay. At some point, there's a deadline. I have to either throw away that data or do something with it. And so you can do almost all that without any explicit system clock dependency, which is kind of nice, except in the one corner case where no data are arriving at all. So in the main loop, I just put together a little diagram of how this kind of works. So this is like a one iteration of the main loop. We create a data region and what I call a state region. And the state region, again, is going to tell me what am I supposed to do with that data. The data capture task fills in that data region. And there's a future there's a future that comes from that task, which I indicated with the diamond, and that's associated with a timestamp. Both the data and the state regions go into one queue, and the future goes into another queue. And at the bottom of the queue, in the same iteration, I take something out of the bottom of the queue. And the reason I use this is because I might use a future that is shifted from when the region was created. Okay, so that allows me to say, well, events have to occur maybe before the data appear. Say if I say everything has to be in place before I start, or I can say events can actually occur. The event deadline occurs after I already have that data. In which case, you have to buffer data a little bit. And then say, oh, I'm not waiting for more events. I'm going to process it. So it's just a simple way of creating that offset. And we also need to know the previous state. Those things get passed to a task, which I'm just calling event log rollup. So that has been receiving events, and it says, given the given state j-1 and the events that have occurred since then, what is this state j? And then we go on and process those two regions. So on the right, it's too small to read, but that's kind of a general flow of the pipeline we have. It's starting up in the very corner. That's the radio camera front end. The data goes through data capture, cross correlation, normalization, flagging, calibration, gridding, which is the computational high nail, and then there's an FFT, and then you're done with the radio camera processor. It gets passed to the post-processing system. So remember I said the states kind of define what I'm supposed to do with that data. And so I may want to do some of these steps, not the others. I may want to do one kind of calibration solve versus a different kind of calibration solve. I may want to be making an image or maybe not making an image. The way this is handled right now is that those conditions are all expressed as predicates, and those predicates are derived from the state. Okay, and so these are all these tasks pretty much are all launched with predicate under predication. I'm going to talk about a different design, kind of reformulation of this that I've been working on that doesn't require predication at the very end. I just want to go into a little bit more detail of how things get parallelized on node, and all this is we intend to have run on single nodes, but it's a Legion program. It doesn't have to, but this is how we expect to keep our costs down and so forth. So at the very top we have the input channels, and there's 40 of them. Those are grouped into what I call streams, and that's defined by how the radio camera front end packs its data together. And then there are subbands, and the subbands are really defined in terms of one of these image products. So one of those image products averages 20 channels. So that's what we define as a subband, and we expect 2 subbands to be processed on a single node. Data capture, it can be, I showed it here as one data capture, that data capture task partitioned into 2 pieces. It doesn't have to be that at all. it may make sense to have multiple threads doing the data capture, so that's a single one. But everything else is pretty much like one for one, right? We can do cross correlation acting on a single channel. Flagging, same thing. Applying calibration, same thing. The narrow line gridding, which is just a one-to-one relation between input channels and output channels. Those are all one-to-one. The big exception, well, there's the one at the bottom, and that's, like I said, the wide average channels, and solving calibration. Calibration likes to get a lot of data. The more data we can get in solving the calibration, the better the solutions will be typically. So we would like to send all the data in this node to do the calibration over a certain time interval. So that's the one that really drives, it makes the most embarrassingly parallel formulation, except for the bottom row, into something that's a little different than that. Okay. All right. So where do things really stand now? We have a lot of these events we've defined, and this is still subject to, operationally what will turns out we're going to need. Yeah. So most of the events are fairly easy to define. The stages, we have a lot of the stages. The big one that we started out with was gridding. And like I said before, gridding is the computational high nail in all this process. And so that's where I actually kind of entered this game, is through gridding. But these others also exist to various states. Well, what don't we have yet? The two big ones are data flagging and solving calibration. Okay, data flagging is primarily to eliminate RFI and also other bad data. Okay, the algorithmically interesting one is the RFI flagging. That is, domain experts are working on this, trying to figure out what to do. Calibration is that's even more the case. And like I said before, there's different kinds of calibration. There's ones that I call modal, which are like, do this kind of calibration while not doing anything else. Do a different kind while not doing anything else. And there's the kind that's continuous. That's mostly driven by ionospheric effects. Yeah, and the others are relatively minor. Applying calibration is actually fairly simple. It's solving the calibration that's a complex problem. So integrating the Legion code with calibration, this is where I'm struggling a bit. So like I said, there's domain experts who are working on calibration code. They go off and they write Python as usual, and they implement something, in this case using JAX and NumPy. And he's put everything together under kind of array distributed actor-based system. So now our first step is to show kind of a proof of concept, because calibration is honestly the biggest scientific question mark in this entire project. Can the calibration be done deterministically in a way that we get the results we're expecting? And so I just have to let this person do whatever they want at this point. They can't even give me requirements. We're just starting to get to the point where they say, okay, these are the requirements. These are the inputs we need. These are the outputs you'll get. So as a first step, I'm just going to come up with some kind of stupid inter-process communication in a Legion task that just is maybe I don't know, an MPI all gather or something like that, and then gets the result back. It's kind of ugly, but I think it's going to be okay. And where I said before that calibration wants all this data, well, it turns out, I think, that a simple average of all those values across all the channels and across the time dimension as well will be sufficient. In which case, it's a small amount of data, but I don't know if that's entirely true yet. Future design, and I say this is desirable, but perhaps unnecessary, depending on how poorly that works or not, we're considering adopting Leagate to do this, because this would allow a nice integration between these Python modules written in NumPy and JAX maybe, um, to be integrated with my code as long as I rewrite my code as a League library. Yeah, and I think, yeah, oh, and the last thing I wanted to mention was the main loop refactoring. So like I said, I showed the diagram of the main loop, and it's really just after it does that, it takes those two regions and passes it to a series of tasks that have that are predicated. So one of the big challenges that I have is making sure that the program execution is running well ahead of real time, right? I want my data capture task to have a region into which to put data before that data arrives. Because if I don't, I'm too late, it's gone. So that's one of the big, it's kind of a challenge that I've found so far keeps popping up when I don't expect it. Okay, I report the difference between when a task runs and what the time is and what the difference is with the real time to keep tabs on that. And every once in a while, make a change, and that just all falls apart. So I think if I keep the main loop to just after I have those after the event rollup task, I immediately pass those regions to just another child task. When that child task executes, there's no more predication. The state is known. I can just put if statements in saying if I'm going to do imaging, then I just do that task. I think that will probably simplify the overall program structure as well. So, but this is kind of, I'm just playing with this at the moment. And I think that's it.